Hello everyone, and welcome to your Historical Geology lecture number 11. We are continuing along with Geologic Time, so now that the midterm's over, we are moving on to kind of what I can say is real historical geology. So what have we been learning so far? Really, it's been kind of like a review of physical geology to get you ready for historical geology. Now, I understand some of you have taken physical geology, some of you have not. That's fine, but now we're going to really get into the material that makes historical geology. So it's the real historical geology stuff. So we start this section of the class off with Geologic Time. You've done one lecture now on Geologic Time, and we're continuing right along where we left off. Do a second one on Geologic Time. So I hope you remember last time we were talking a lot about layers of rock, what we call strata. So you can see the layers of rock here. And you can see that those sedimentary rocks continue for vast stretches of time and space. So you can see that this sedimentary rock layer, you might be able to find it all the way back over here somewhere. Okay, in these mountains back behind us. You can see this layer right here very clearly extends like this, right? And you can see it back here, and you can see it all the way, really clearly, all the way back here. Okay, so they extend over these vast areas, okay? And the principle behind that, I hope you remember the stratigraphic principles of Steno. One of them was lateral continuity. So this picture is showing lateral continuity in action. Okay, so the sedimentary rocks were laid down at a certain depositional environment, whatever it was. Maybe it was a desert. Maybe this is sandstone. Maybe this is siltstone. I don't know what it is. I can't really tell from here. But it was laid down in a certain kind of depositional environment. And that depositional environment stretched over vast areas. Okay, so anyway, kind of where we left off is we were talking about this problem. And it's very important, and it's kind of a subtle idea, so I want you to try to pay attention and learn this. It's a very important idea in historical geology, and it's also sort of, I guess I could say, a subtle idea, so it requires you to think kind of carefully about it. So this is the problem here. We look around the world right now, and we can see that there's right now different depositional environments in different places. Maybe if you go to Louisiana right now, you'll find swamps. Okay, swamps. Okay, when you have a swamp, the kind of rock it lays down is coal. Okay, so right now we have swamps in Louisiana and other places that are creating coal. Eventually will become coal. Okay, we have places, let's just imagine this is in California. And you have a desert environment here, and maybe that's laying down, maybe it's rock salt, or maybe it's gypsum. Okay, chemical sedimentary rocks. Maybe another place right now, maybe this is Michigan. Okay, I don't know, but I'm not sure exactly where this is, but right now this is a polar, not polar, but it's a cold, icy environment here. Maybe it's laying down, I don't know what, maybe it's siltstone here. I don't know. I can't really tell what is being laid down here, but anyway, the problem is this. You go around the world, there are different depositional environments in different places, and they're depositing different kinds of sediment and producing different kinds of rocks. But they're all doing it at the same time. So the problem is this. When we go around and we look at rocks in different areas, sedimentary rocks, those rocks could be of the exact same age, laid down at the exact same time. But we don't know, how do we know that they are of the same age, right? Because different places are doing different things at different times. Does that make sense? So we could go into the rock record. We could look at, a sandstone in, let's say, a sandstone in Michigan, and a sandstone in Wyoming, and a sandstone in Florida. How do we know that and maybe they're all the same age, but how do we know they're of the same age? How do we know? So the answer to that is it's fossils. Okay. You know, life has changed over the course of geologic time. Originally, we have a lecture on evolution, you know, and I explain a little bit more how life has changed over time. But suffice to say, I hope you know that life has changed over time. You know, it hasn't always been the same. We have different kinds of organisms living at different times. Okay, so right now, you know the kind of animals that are alive right now, and those animals have changed over the years. You know, it weren't always, you know, elephants and hippos and rhinoceros in Africa. There wasn't always bears and mountain lions and deer in North America. It wasn't always the case that there were, you know, et cetera, panda bears and things like that in China, right? Those different animals have changed over the years. Okay, so we're going to use those changes in life to pinpoint the time that geologic formations formed. Okay, we're going to use those fossils and the fossil assemblages to pinpoint what geologic age is represented by different rocks. Okay, and that's how we're going to figure out rocks all around the world. We're going to figure out that, yes, this sandstone was made at the same time as this limestone in Florida. This siltstone from Wyoming was made at the same time as this evaporite deposit in California, et cetera, et cetera, et cetera. Okay. So that kind of dating is called relative dating. Okay, that's an example of relative dating. And it's relative because when we use fossils to date rocks, it doesn't tell us the exact age of the rock. Like, we don't know, like, okay, yeah, this rock is, we find this ant, okay? We find this ant preserved in the fossils. This rock is 150 million years old, plus or minus 1, you know? It's not like that, right? It just gives us kind of a bracket of ages, okay? We only know that this is of the same age as other rocks that have fossilized ants in them, okay, if that makes sense. So one of the first gentlemen to do this and use fossils in order to date rocks was this gentleman. This guy is William the Strata Smith. They really called him the Strata. Okay, William the Strata Smith. Okay, oh yeah, there it is. I have it written right there. So this is 1815, an English gentleman, and had a lot of spare time on his hands. And he was one of the first people to use fossils and fossil assemblages to date the rocks. And he used Steno's principles of sedimentology, his principles of superposition, and reasoned that fossils found in lower sequences of strata are older than the fossils found in upper sequences. Okay. So had this very, very famous first map of the Earth in 1801, inspired by the science of geology. This is one of the first geologic maps ever created. So he's very famous for this. Okay. So we use fossil assemblages to figure out what the time period is that a sedimentary rock was created. So, by the way, sedimentary rocks are the only kinds of rocks really to have a lot of fossils in them. Igneous rocks don't really have fossils. Sometimes they do. Sometimes volcanic beds can have some fossils in them. Sometimes it's rare, but that does happen. Sometimes you can get even metamorphic rocks with some traces of fossils in them, but it's rare. By and large, sedimentary rocks are the rocks that contain fossils. So I just want to say this loud and clear so you all know, because this is going to be on the test and on the final exam. Sedimentary rocks are the rocks that generally contain fossils. Okay. So fossil assemblages succeed one another through time in a regular and predictable order. Okay. And what you're going to find is that animals, generally they become more complex as we move through time. So animals get more and more and more complex. They start to have, every age there's a new evolutionary novel structure that originates, and they can get more complex through evolution. Okay, so anyway, what you're going to find is as you move through time, you're going to have different assemblages of different fossils in different ages. Okay, so maybe in the oldest strata of rock, you have this assemblage of fossils. As you move through, you get this one. As you move through, you get this one. Shells are very commonly found in sedimentary rock fossils because, I don't know if you know anything about how clams and other mollusks live, but the way that they do things is they bury themselves in the sediment, and they filter feed from their buried position in their protected shell. So fossils, shelled animals like mollusks, commonly form fossils this way. So rocks from different areas with the same kinds of fossils are the same age, okay? That's the thing I want you guys to remember, okay? Rocks from different areas with the same kind of fossils are probably of the same age, all right? And that's how we relatively date different rocks from different places, okay? So, biota has become more complex through time. So we've determined this for both plants and animals. They become more complex. So we find that older fossils, older rocks, are more simple. They contain simpler animals. They get more complex. Going from very simple animals such as sponges. I don't know if you're aware of things like this, but things like sponges and corals, they are types of animals. Okay, so they're very simple types of animals. They're most basic kinds of animals. And then we get more and more complex, mammals, amphibians, birds, humans. Things get more complex as you go through the rock strata to progressively younger and younger, and strata that are progressively higher in the stratigraphic record. Okay, and same things with plants. You end up with very simple plants at first. Okay, you have things like club mosses, horsetails, ferns, and eventually you get more and more evolutionary novels. Like you get fruiting seeds, you get flowers, things like that, and you start to have pine trees, ginkgos, flowering plants. So things get more and more complicated and complex as you move through the stratigraphic record, higher and higher in the stratigraphic record. So on the bottom you find older rocks with simpler organisms. As you move up, you find younger rocks with more complex organisms. Okay, so I hope that all makes sense to you. Oh, I got to erase everything on the slide here. There. All right, so observations of fossils in older beds versus younger beds clearly demonstrate that biota life forms have changed. Okay, so if we look in the fossil record, we look at we find different kinds of animals in the fossil record, and some of them are not around anymore. For example, rocks of the Paleozoic era are filled with trilobites. Okay, they were a very common animal at that time, but they're not around anymore. We don't have any trilobites living anymore. We have horseshoe crabs that look a little bit like trilobites, but they're not trilobites. Okay, they were very, very common in the Paleozoic. They were maybe one of the dominant species of the Paleozoic, but they're gone now. Okay, so we see that life has changed, right? Brachiopods, this organism right here, I know that you're probably looking at this and say, that's a clam. That's not actually a clam. That's something called a brachiopod. Now, this is something we would have learned if we'd done our evolution lecture, but we didn't do that, so I have to kind of show you these things as we go on. So this is a brachiopod, and by the way you know it's a brachiopod is because it has symmetry, a line of symmetry down the middle of its shell like that. Actually, clams, if you look at clam shells, a lot of them kind of look something like this. Okay, that looks like that's like a clam shell. Okay, that's like the top of the shell, and you can see that it does not have symmetry going down the front of the shell, the top view of the shell. Right, brachiopods do, so they're different. Brachiopods are actually a totally different phylum than the like clams that we have today. Okay, so brachiopods are still around, but they're not prolific like they used to be. Okay, they used to really be like king of the oceans, but they're not anymore. So anyway, we find that life has changed over the years, right? When we go to the Mesozoic, we find dinosaur bones. We don't find dinosaurs anymore, obviously. Okay, you go looking even in relatively recent beds, we find saber-toothed tigers, right? Mastodons used to live down here in Corpus Christi, but we don't find them here anymore, right? So life has changed, and we can see this happening real time, right? You see the ranges of animals changing. We see different animals going extinct. we actually see new types of animals, new species coming into existence. So this is all stuff we would have talked about in the evolution lecture, but we missed it. So I'm kind of going over it a little bit right now. So biota has become more complex. The assemblages of biota are recognizably different over time. Animals change over time, plants change over time. Okay, we see successions of different animals starting with simple in the oldest strata, going to more complex as we move through. And we also find that the relative ages of fossil assemblages can be determined. So we can figure out that, yes, indeed, these two pairs of rocks with the same kinds of fossil assemblages happened at the same time. By the way, a fossil assemblage just means groupings. Assemblage is just, a set of different fossils, okay? A set of various fossils we find in the same rock. So if a rock has the same sets of fossils, they're probably of similar ages, okay? So, for example, and we can do this very subtly, like we can see very subtle changes in trilobites through time. And we can figure out which are the older kinds of trilobites and which are the younger kinds of trilobites, okay? So just by the shape of the trilobite fossils, they're very useful for figuring out how old the rocks are. So strata with the same fossil assemblages have the same relative ages. So we might have two. Now you see, this is something you got to pay attention to because you have an exercise, a pretty difficult exercise in your lecture assignment this week, okay? And in that exercise, you're given three different kind of outcrops, okay, showing different strata. And you have to figure out which strata are the same age using the fossil assemblages. Now here, you're given, this is really the easiest one you could possibly have. Here you have two strata, two outcrops, okay, with different strata, okay? Now, very simply, you see that the fossils in this one, this kind of orangish color, are the same as the fossils in this one. So we know that these rocks are of the same age, okay? That's the simplest kind of example I can give you of something called correlation, okay? Correlation. Correlation is when you can correlate two different strata of rock and recognize that they are of the same age based on similar fossil assemblages, okay? So hopefully that makes sense to you. So we can look at these guys and see that, yes, in two different places, two different outcrops, we find that even though these are different kinds of rocks, we find that they have the same fossils, okay? So we can recognize that this layer of rock is the same as this layer of rock, okay? That's called correlation. So here's another example that shows how fossils can be used to correlate strata over a widespread area. So we might have outcrop ABC, and between here and between here, and between here and between here, and between here and between here, we all find the same fossils, right? We find this kind of what looks like kind of a bivalve, a trilobite. This is probably some kind of rugose coral. We all find this in these rocks. But look, these rocks are different, okay? This is a sandstone, this is a siltstone, this is a limestone. Okay, this is a siltstone, this is a limestone, this is a sandstone. This is siltstone, this is limestone, this is siltstone. So you might look at these and be like, no way, hey, no way that these rocks are the same age because they're all different, But remember that different areas are laying down, they have different depositional environments. So you can't just look at the kinds of rocks and be like, hey, this is the same unit of rock. You can't do that. So you can correlate them through the fossil assemblages. And you see these rocks have the same fossil assemblages here. So we can correlate this group of strata, okay? We can correlate this is a siltstone here. We can correlate that with this layer, or actually a couple layers, and correlate it with this layer because they all have the same fossil assemblages. So we know that even though that they're different rocks and different sets of rocks, they're the same age because they have the same fossil assemblages. Okay, I know I keep repeating myself over and over and over again. It's just because this is it's really actually a pretty difficult idea to get into your head. So That's why I keep saying, kind of saying the same thing over and over. Okay. So take a look at this again. You know, we can correlate. We might see, hey, this olive green colored rock. We have an olive green colored rock over here in location 2. Location 1, we have an olive green colored rock. We have an olive green colored rock in location 2. Are they the same age? Well, in this case, they are, because look, they have the same kind of fossils in them. Okay, but then directly underneath that, does that mean that this rock directly underneath is the same as this? No, because look, we have different fossils in this stratum, in this layer, as we do in this layer. We have different kinds of fossils, see? So that wasn't of the same age. This correlates, this blue color correlates to that blue color, okay? So you can't just look at the sequence of rocks without looking at the fossils in order to pin down ages, see? So anyway, that's how it is. Hopefully I made my point. So these strata, right, of rocks, these outcrops of rock might be separated by large distances, but we can still figure out that they're of the same age, because why? They have the same fossils, right? They have the same fossils. So both those orange beds are found and have identical fossils. They're the same relative age. Okay. So because of the work of Stratosmith, we now have established fossils as a means of relative age dating, and we can make meaningful geologic maps that correlate rocks of the same relative age. Okay, even though they might be different kinds of rocks. You know, maybe here in Texas you have a rock, maybe it's 100 million years old and it's a sandstone, but we can correlate that with a siltstone in Michigan that is, 100 million years old as well, because we can use fossils. Okay. So this is one of the first geologic maps ever created. Again, it was created by William the Stratosmith, and correlates rocks on either side of the English Channel. So some of them in France, some of them in England, but he finds rocks of the same age or similar ages. Okay. So relative ages can be determined from a record of, we have identified in paleontology, we've identified 250,000 different fossil species. Okay. Keep in mind that this represents, how many different animals and organisms are there right now? I don't really know the answer to that, but it's millions and millions and millions. I think it's like probably something like, maybe tens of millions. So the fact that we've only discovered 250,000 fossil species means that probably we are seeing just a drop in the bucket. It's really kind of amazing. Like, we go back and we try to imagine what life might have looked like. And you're going to see this as we march through time. We're going to say this is maybe what life looked like 500 million years ago. This is maybe what life looked like 600 million years ago. What it looked like 100 million years ago. But really, we know nothing. We have 250,000 fossil species. And there were probably billions, like there was probably billions with a B, different species that have lived over Earth history. We found less, I'm sure that we found less than 1% of them. So there's so much we don't know. We just see dimly through kind of a tarnished mirror. That's all we really are seeing when we look back through the fossil record. We see very little. It's just a little, but it's enough to get an idea of what life was like. But there's so much we don't know. So from the kinds of rocks we find, from the kinds of species we find, we can figure out what the past depositional environment was. We can figure out if it was a swamp, or if it was an ocean, or if it was a shallow or deep ocean. We can know that, actually, because different, I'm sure you guys know who fish, that different animals live in deep water compared to shallow water, right? You find here close to the shore, you find different kinds of species of fish, right? You find redfish and red drum, black drum. You find spotted sea trout, right? But if you go out to deeper water, you don't find those anymore. You find different kinds of fish. You find snapper, you find tuna, okay, sharks and things. You find different kinds of species in deeper water. So we can even look at the fossils, figure out how deep water was. Was deep marine or shallow marine, things like that. We can figure out from the fossils, how old something is. We do that using something very special. I haven't talked about this yet, but we do it using index fossils. So certain fossils are very indicative of certain time periods. We can use that to figure out exactly what time period a rock was formed during. Okay. So take a look at this. I want to point something out to you. If you take a look at this to kind of illustrate the idea of index fossils. So look at this strata. You find, let's see, let's find something here. Notice that you find these guys, fossil C. You find them from here all the way down to here. Okay, so you find them over a pretty wide area. But these guys, fossil D, you only find in this particular time period. So fossil D is a good index fossil, okay, because they have a highly restricted time period that they existed in. Okay, so those make good index fossils because they only existed during a very certain specific time. Okay, so just kind of give you a layout things. The first shelled organisms we find in the Cambrian, 540 million years ago to 490 million years ago. The first fish we find in the Ordovician, 490 to 440 million years ago. The first land plants we find in the Silurian, 440 to 415. The first amphibians in the Devonian, 415 to 360. So we're going to go through all this stuff in great detail. So you don't need to get it right now, the time periods that these things formed in, but it's going to be coming down the road. Okay. So let's move on to something called unconformities. Now this is another exercise that is on your lecture assignment. It's kind of a big exercise. So the fact is that at a particular place, let's say that you're depositing sand, okay, and the sand layer forms, another sand layer forms, another sand layer forms, another sand layer forms. Let's say that this is an ocean, okay. Let's say it's it's corpus. Let's say it's a beach. Okay, so here's the water. And let's say, I'm going to get, let's say here's the shore. There's the ocean bottom. And what's happening? Well, sand, you know how it is at the beach. Sand gets deposited, right? We're depositing sand at the beach. So sand gets deposited here, gets deposited, gets deposited, gets deposited. And what's going to happen? Eventually, sand is going to build up and build up and build up. And eventually it's going to be above the water level, okay? And once it's above the water level, deposition stops. Okay, it stops. So maybe this sand formed, at time 1, this formed at time 2, time 3, time 4, time 5, but then deposition stops because we're above the water level, okay? So the sand isn't going to get deposited there anymore. Now let's say that 100 million years later, the water levels rise. And now the water level's up here again. So then what's going to happen? Well, deposition is going to resume, but it's going to be, let's say now it's a different kind of rock. Maybe now it's putting down silt instead of sand, and it's deeper marine. So then you get silt on top. Okay. But now you went from time 1, time 2, time 3, time 4, time 5, but then deposition stopped for a long time. And maybe now it's skipped, tens of millions of years. And now this is not time 6. This is maybe like time 10 and 11 and 12 and 13, et cetera, et cetera, et cetera. So there was missing time, okay? There was, between the silt and the sand, there was missing time. So deposition wasn't continuous, okay? That line right here where there's missing time is called an unconformity. Okay, so that's a little introduction to that. Let me go through this in greater detail, okay? So if you look at an outcrop of rock strata, do you think that the rocks, you see all the different rocks here, all the different layers, every layer represents a different time. Do you think that every rock from every age was necessarily preserved? Okay. And the answer is no. Sometimes there's missing time. And that missing time is called an unconformity. Now, how do you know that there's missing time? Well, we're going to go over that now. So let's say that we have, let's take a look at this. This is a real outcrop from Texas, okay? So it's a road cut from Texas. We see deep water limestone here. No fossils. Then all of a sudden on top, we see shallow water limestone with fossil oysters, okay? So something changed between these two rock layers, okay? Because you know oysters don't really form in deep water, right? They form in shallow areas, okay? So the oysters, obviously it means that water levels changed, and maybe they changed instantaneously, but maybe not. Maybe there was missing time right here, okay? So that could be a kind of unconformity where you see this pink fuchsia colored line right here, okay? Obviously something changed to upset the ongoing depositional sequence between that upper and lower strata. So this kind of red line surface is a time of non-deposition, or maybe is it just a period of erosion of the existing strata, or both, you know? So you know, what could have happened? This limestone, maybe deposition stopped, and maybe there were previously layers, more deep water limestone on top, but maybe this got exposed to the open air and got eroded away. And then later the shallow sea came and deposited this shallow water limestone on top. So there could have been erosion. There could have just been a cessation of deposition. We don't know, but there's something going on here though. So we have a period of erosion on the upper surface, or maybe no deposition of sediments for millions of years, or both. We don't know. But something happened to upset the normal pace of deep water limestone deposition here. Okay, something changed. Maybe water levels just changed drastically over a short period of time. We don't know exactly. So this upper surface would be referred to as an unconformity. Okay, so it's an unconformity because it's not, this lower bed is not conformable with the upper bed. Conformable means that there's no cessation in deposition. It's continuous deposition. That's what conformable beds are. That means that there was no cessation in deposition. There's continuous deposition from bed to bed. But there was obviously some kind of cessation of deposition at this point. Okay, so that's what makes it an unconformity. Okay, so understanding unconformity is critical to our understanding of geologic time and geologic history. So there's some time that was missing here. Okay, it's called an unconformity. Means that time is missing, right? An interval of geologic time is not represented by any strata in this area. So unconformity, very famous place, very famous unconformity in the history of geologic sciences is Siccar Point in Scotland. This is where James Hutton, you might remember we introduced James Hutton in one of the previous lectures, came up with his ideas of the vast stretches of time, right? And he came to some of those conclusions here at Siccar Point in Scotland. And you can see there's an unconformity. You can actually see it right here. Okay, I'm going to show it to you. Look at these beds. See how these beds are kind of oriented like this? Do y'all see that? They're almost vertical. Can y'all see that? Okay. So those beds are almost vertical. At some point they got tilted, okay? Now looky here. Look at this. Right here, I'm going to draw this in another color. On top of those beds, you see other beds of rock. And they are oriented like, look at the strata, are like this. Okay? So do you see that there's a different angle here? So I'm going to draw in a different color here to point this out. I'm going to maybe do purple here. Okay, right here in this purple line, you see rocks of one angle hitting rocks of a different angle. Okay, that is an unconformity. That's an unconformity. So it's called an angular unconformity because something happened. You know, the rocks were deposited, they got tilted. Other rocks were deposited on top later at a different time and got tilted. Okay, so we know that there must be missing time at this point that I drew in purple. Okay, so there's an unconformity there. Okay, and these are actually about 435 million year old. These are about 370 million year old layers. Okay, so the way that angular unconformities work is that maybe at time 1 you got a bunch of sediments that get folded. Time 2 they get eroded, so we're missing time. And then time 3 you get new deposition. Okay, so this is the time interval, time 2, that is not represented because instead of deposition, continuous deposition, we have erosion. Okay, a nonconformity is a different kind of unconformity. Okay, so there are different kinds of unconformities. Okay, they're all called unconformities. Angular is one. Okay, angular unconformity is one. A nonconformity is different. In a nonconformity, you have a pluton maybe that intrudes sediments, and then erosion of the basement rock. You know, erosion occurs and the basement rock is exposed, and then new deposition occurs on top of the plutonic granite rock. Okay, so when you have sedimentary rocks in contact with either gneiss or some kind of granite or a plutonic or metamorphic rock, you know that there wasn't continuous deposition. Okay, so this was, yet again, represents an unconformity, and this kind of unconformity is called a nonconformity. Now the last kind is one that I've already showed you. Okay, this kind. Okay, this is an unconformity. More specifically, it's called a disconformity. A disconformity happens when there's deposition. Okay, so you get deposition, 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 deposition. But then something happens, maybe the water level drops and erosion occurs. And you get erosion of this layer gets eroded off right here. And then water levels rise again, and then you get deposition resume, and you get different kinds of rocks put on top of those older rocks. But there's time missing here at time 2. This is pretty hard to recognize, but it does occur. So this is called a disconformity. It's the third type of unconformity. Okay, it's the third type of unconformity. So there are 3 types of unconformities. Angular unconformities, that's where you have rocks of different tilts, different angles, lying on top of each other, like Sychar Point. There's nonconformities, that's when you have sedimentary rocks lying over older igneous or metamorphic rocks. And disconformities, that's when you have previously deposited sediments that have been eroded and there is deposition on top of an eroded surface. So I'm going to show you kind of like 3 little videos. I tried to turn the volume up really loud, so hopefully it'll pick up on the microphone. I'm going to kind of show you these different types of unconformities with a video. Okay, so disconformity, nonconformity, angular unconformity. So those are the 3 types of unconformities. Okay, 3 types of unconformities. So there's your disconformity. Okay, that's where the beds remain parallel. See how the beds are still parallel, right? They're still the same angle, right? You could see the same angle here. You would not necessarily know that there's even an unconformity here, right? It's hard to recognize. So disconformities are hard to recognize. Again, with disconformities, the beds remain essentially parallel across the unconformity surface, but we're going to be looking maybe at there's a sudden jump in the fossil assemblages, and we can maybe tell. Sometimes we find pieces of this rock in this bed. That would be an indication that erosion occurred, and that's how pieces ended up in there. Okay, that's another indication perhaps an unconformity occurred. So critical point here, all rocks, upper and lower, are sedimentary rocks. Okay, so when you have sedimentary rocks on top of sedimentary rocks of the same angle, you know, there's no tilt or angle difference between the layers of deposition. That means that's a disconformity. Okay, so here's a disconformity. I'm going to try to play this. Hopefully it's loud enough to hear.
An unconformity between 2 sedimentary rock sequences is called a disconformity. Let's reconstruct how this particular disconformity formed. When sea level was high and an ocean covered the area, several marine sediment layers were deposited and lithified into rock. As sea level fell, the rock layers were exposed subaerially, and an erosional landscape formed atop the sequence. After millions of years of erosion, sea level rose again and covered the region anew with a shallow sea. New layers of marine sediments were deposited and lithified. The former marine rocks are now once again exposed subaerially, and the disconformity is evidence of at least two separate incursions of the sea into this region.
Okay, so that was a disconformity. Okay. Now, a nonconformity, again, is when you have sedimentary rock layers that are sitting on top of either a plutonic igneous rock or they're sitting on top of a metamorphic rock, what are called basement rocks. Okay. Sometimes they're called crystalline rocks. So nonconformities are erosional surfaces that are cut into metamorphic or igneous rocks that's then covered by sedimentary rocks. Okay, so for example, this granite is overlain, right? Here's your granite, and it's overlain by sandstone layers. Okay, you can see how the sandstone has layers. The granite does not. Do y'all see how the granite has no layers in it? That's because sedimentary rocks form layers. Granite, metamorphic rocks don't have layers like that. Okay, let me erase the ink here. Okay, so metamorphic rocks lying beneath are different. Thus, they're not in conformity. They don't conform with the overlying sedimentary rocks. So, those represent a nonconformity. Okay, so this is a very famous picture from the Grand Canyon. This is the Vishnu schist here, below this stuff here, and there's sandstone layers lying on top. Okay. So lower rocks are not sedimentary. They're either plutonic igneous rocks or they are metamorphic rocks. By the way, I just want to emphasize something. You cannot forget what we learned in the first half of this class, right? Because you're noticing I'm constantly referring back to stuff that we already learned about, right? We talked about plutonic rocks. We talked about metamorphic rocks, and you got to remember what those terms mean, because I'm just going to throw terms around like that, plutonic rocks, and hopefully you remember what that means, okay, and how those kinds of rocks form. So here's a animation shows how nonconformities form.
An unconformity between non-sedimentary rock layers, such as igneous or metamorphic rocks, and sedimentary rocks is called a nonconformity. Let's reconstruct how this particular nonconformity between granite and sedimentary rock formed. When sea level was high and an ocean covered the area, several marine sediment layers were deposited and lithified into rock. This thick stack of sedimentary rocks was then intruded by a granite pluton. Long after the intrusion had cooled into granite, erosion cut down into the intruded rock layers. This ultimately led to the granite being exposed at the surface. After millions of years of erosion, sea level rose again and covered this granite terrain anew with a shallow sea. Today, marine rocks above the granite attest to a long history of deposition, intrusion, erosion, and a subsequent repeated incursion of the sea into this area.
Okay, so that's what's called a nonconformity. Okay, so again, a nonconformity is a type of unconformity. A disconformity is a type of unconformity. The last kind of unconformity we're going to talk about, I think it's the easiest to identify. It's called an angular unconformity, which is a type of unconformity. So an angular unconformity is when an erosional surface cut into folded or tilted strata over which younger strata were deposited. So you can see that the angle here of these strata, it's like this. Okay, right, like this. And the angle on top is like, it's almost parallel, okay? So you can see there's a difference in the angle there. All right, so let me erase everything on here. Okay, so again, that's an angular unconformity right there, okay? So let me play a little video for you.
An unconformity between folded or tilted rock layers below and horizontal sedimentary rock layers above is called an angular unconformity. Let's reconstruct how this particular angular unconformity formed. When sea level was high and an ocean covered the area, several marine sediment layers were deposited and lithified into rock. These rock layers were then deformed during a regional mountain building event, forming anticlines and synclines. These folded rock layers were exposed subaerially, and an erosional landscape formed atop the sequence. After millions of years of erosion, sea level rose again and covered the region anew with a shallow sea. New layers of marine sediments were deposited and lithified. The former marine rocks are now once again exposed subaerially, and the angular unconformity separates those layers below who have experienced a mountain building event from those above, who were last deposited in a shallow sea.
Okay. So that's a angular unconformity. So this is how you identify those kinds of unconformities. A disconformity consists of just sedimentary rocks. Okay, except that, and you know, also the sedimentary rocks are the same kind of tilt or same angle. Okay, so that's the hardest one to identify. But it consists of just sedimentary rocks at the same angle. Nonconformity consists of sedimentary rocks on top of a granite or on top of some kind of metamorphic rock, or plutonic or metamorphic rock. Angular unconformity happens when you have sedimentary rocks of one angle hitting abutting rocks of a different angle. Okay, so they're all sedimentary rocks, but they're at different angles. Okay, so again, that basically represents missing time. Okay, so there was time missing in that sedimentary sequence. So what kind of unconformity is found between the two red lines? Take a look at that. So we have Mississippian shale. Then below that we have Devonian carbonates. And above that, right, we have something else. I can't tell what. But what's going on here? Okay. These are sedimentary rocks. You can see the layers, right? Do y'all see the layers? Carbonates, these are limestone rocks, okay? These have layers, they're sedimentary rocks. So what happens when you have sedimentary rocks on top of sedimentary? Is the angle different? Is the angle between the Mississippian shale and the Devonian carbonates different? No, it's the same. It's all the same. So this is a disconformity, okay? It's because all of the beds are sedimentary rocks and they're all parallel, okay, but there's missing time there. Now let's take a look at this. We have sedimentary rock layers sitting on top of metamorphic rocks. What kind of unconformity is that? That's a nonconformity, right? That one's pretty easy because, you know, metamorphic rock, if it was plutonic igneous rock, that would tell you something too. It's nonconformity, okay? So you can guess probably the next one's going to be angular, right? Sycamore Point. So that's a different again, a different angle. You can see the rock layers here are almost vertical. And they're coming into contact with rock layers that are like this. So you can see that right here, that's the angle of the bed, and then the angle of the bed here is like that. So they're different. You know that's an angular unconformity. Okay. So let's talk a little bit about, I know there's a long lecture, but let's talk a little bit more about correlations. Okay. So stratigraphic formations are intervals of strata with specific rock types that can be traced over a fairly large region. Okay, so stratigraphic formation, so like a rock formation, okay, is a sequence of rocks that can be traced over a large area. Okay, so for example, sometimes you'll hear me say things like this: the Kaibab limestone, right? the Vishnu schist. Okay, these are rock formations. We give them names like this so that they can be identified more easily. Okay, so we'll talk about the Kaibab limestone, or whatever. Later we'll talk about the St. Peter sandstone. We'll talk about the evaporites of the Permian Basin. We give them different names. But anyway, they exist over very large areas. Okay, and we have to correlate those in one area to another area. So this might be the same limestone, and we might find it. We can actually find this in California, and we can find it in Nevada, and we can find it in Arizona. Okay, this Kaibab limestone. Okay, but how do we know it's the same? So that's where the whole art of correlation comes in. Okay, so we can find this limestone in different areas over vast regions. Okay, but we have to correlate that limestone to all of its different locations. So when we recognize that is the same Kaibab limestone, it's the exact same rock, it's just in different areas, different exposures in different parts of the country, that's what correlation entails. Okay, so a very important scientist in this is Johann Lehmann. Notice that groups of rock can be found over long distances, hundreds of miles away, and he called this correlation. So it's the same rock, it's just in different places. Okay, so we can look at this strata, this pink strata right here. Notice it's the same as this one right here. It's the same as this one right here. It's the same as this one right here. Okay, so just because it's not connected doesn't mean it's the same. It's the same rock, right? This white sequence here, white striped sequence here, is the same as the one here. It's the same as the one here. Same as here, same as here, right? It's we can see it over here, right? So just because, again, it's not connected doesn't mean that it's not the same rock. It's just that erosion has separated. One time it was continuous, laterally continuous, but it's been separated by erosion. Okay, so we can recognize, for example, if we go to the Grand Canyon, we get all these. Maybe we get all these different rock layers preserved, right? All on top of the Vishnu schist. Okay, and we can actually find these rock layers in different places. You can go to California, you can find the same thing. You can find little bits of the Kaibab, little bits of the Redwall limestone, a little bit of the Tapeats sandstone, right? You can find it different, but you'll notice that there are vast regions that have no rock preserved even. So you're just preserving different parts of that sequence in California. Okay, so a lot of geologic time is lost, in unconformities. Okay, it's little, like I said earlier, it's like we see the past dimly, just through kind of like a tarnished mirror. We get these little glimpses of it, and we can put a lot together. There's so much we don't know, and a lot of time is not represented. So again, it's just you can correlate these different groups, the Supe, the Monte Cristo, the Temple Butte, the Moave. You can correlate these different formations in Las Vegas, okay, with different ones in the Grand Canyon, for example. Okay, so it's this whole art of figuring out which rock formations, recognizing them across these really broad regions, right, in different continents, different countries, different cities, etc., etc. So that's called stratigraphic correlation. Okay, determining relative ages of strata at different locations, and we've talked about this already. So I want to go over kind of, like I said, you have an exercise on your lecture assignment that's pretty difficult. Disappointingly, a lot of people kind of skip this stuff. I made it worth a lot of points, so I really highly recommend you don't skip it, because it will be on your final exam. You will have to do this, so it's not going to go away. And by the way, it's worth a lot of points on your final exam. I think last semester I made it 10 points or 15 points. It's a big high point exercise, so you need to know how to do this. Okay, and it's not really that difficult. I know it looks intimidating, it looks daunting, but it's not that difficult. So imagine you have three different locations. Okay, let's say this location A, B, C, and you have different rocks at every location. Okay, and we have to correlate the different rocks. So again, it's very simple. We're just going to look at the fossils. So this one with the sea stars, they all correlate, right? So this is all the same. So the way that you're going to do that is you're going to draw lines kind of like this. Okay, that's how you would do that. So that's how you would do it on your exercise. Okay, so you draw lines like that. And then we're going to correlate, right? You can see that these have the same fossils. So you can correlate, you draw a line like this, correlating with a line like that. Okay, now you'll notice that this rock correlates here. Okay. But you'll notice that there's none of this blue rock is here in location A, core number 1. Okay, so that's how you do that. Okay, and you might know by the way, because I do ask about this. I say, show me where there might be unconformities. Okay, well, you know that there must be a disconformity right here, right? Because there's missing time right there. So anyway, that's how you do that. Okay, it's not. And now this is actually easier example than what is on your thing. But anyway, that's how you basically do that exercise. And by the way, in that exercise, I ask you point out unconformities. There's some places where you'll find angular unconformities, like it'll have the strata kind of shown like that. You know that there's an unconformity there. Okay. They also help you in that exercise. Giving you some volcanic beds that can be radiometrically dated, so it also can give you an indication that there's there's missing time, different places. So I think I will release a video. I think I might still have it from last semester that shows how to do that exercise, and I'll release that. So can I give you more pointers about it? Because I know it's a daunting exercise, but it's really not that hard. Okay, we have to talk about geologic time now and the geologic time scale. So I showed you this, I think, at the beginning of the course, but now time has come that you need to know it. Okay, so let me show you what you need to know. Okay, we split time up. We did talk about this kind of near the beginning of this course. We split up time in 4 different ways. Okay, we have eons, eras, periods, epochs. Okay. We split up all of Earth history into 4 eons: the Phanerozoic, we're in the Phanerozoic right now, the Proterozoic, the Archean, and the Hadean. And we're going to go through each of these eons in turn. So we're going to talk about the Hadean, then we're going to talk about the Archean, then we're going to talk about the Proterozoic. Then after that, we're going to move on to spend most of the class on the Phanerozoic, and we're going to talk about the Paleozoic era, the Mesozoic era, and the Cenozoic era. Okay. Now, and we're going to talk about, for each of these, we're going to talk about the geology that occurred during that time, the geologic changes, and we're going to talk about the changes to life. Now, we split up every eon into eras. You do not need to know the eras of the Proterozoic, Archean, and Hadean. You don't need to know those eras. You just need to know the eon name. You do need to know the eras of the Phanerozoic eon. So you need to know Cenozoic, Mesozoic, Paleozoic. You need to know that eras are split into periods. You need to know the periods of the Phanerozoic, okay? You don't need to know any of this stuff. You don't need to know periods of the Proterozoic, Archean, or Hadean. They are as follows. For the Paleozoic, it's Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. We lump the Pennsylvanian and Mississippian together as the Carboniferous, okay? In the Mesozoic, you have probably more familiar terms to you: Triassic, Jurassic, Cretaceous. And then the Cenozoic, we split into the Neogene, Paleogene, and the Quaternary, and we lump the Neogene and Paleogene together as the Tertiary. Okay. Now, you do not need to know the epochs of anything besides the epochs of the Cenozoic, which are the Holocene, Pleistocene of the Quaternary. Holocene is right now. We're in the Holocene. Pleistocene is basically, you can think of the Pleistocene as the Ice Age. Then there's the Pliocene, the Miocene, the Oligocene, the Eocene, and the Paleocene. Okay, so you need to know those. I suggest coming up with some kind of mnemonic device that is easy for you to remember. You do not need to know any of the times, except you need to know this time at what's called the KT boundary. This is the KT boundary. Okay, K is for Cretaceous, T is for the Tertiary. Okay. So I know that obviously Cretaceous is spelled with a C, but this was invented by Germans who spelled it with a K. So the KT boundary, you need to know 65 million years ago. That was that. Okay. You need to know the Permian, what's called the PT boundary, okay, PT Permian-Triassic boundary. That's 251 million years ago. Okay, you need to know that. And you definitely need to know this. This is the Cambrian explosion, the 542 million years ago, the beginning of the Phanerozoic, okay? Those are the dates you really, really must know for this class. And then you should know these dates right here. 2,500 million years ago, that's the same as 2.5 billion years ago for the beginning of the Proterozoic. 4,000 million years ago, which is the same as 4 billion years ago, that's the beginning of the Archean. And of course, 4.5 billion years ago, 4,560 million years ago for the beginning of the Hadean. Okay. So anyway, yeah, you need to know all that stuff. It will be on the final exam. You will be tested on with a blank geologic time scale. You need to know this stuff. Okay. So just to kind of let you know, there are just some different mnemonic devices you can use here. You know, Cambrian, right, to know the periods. Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. Okay, come over someday, maybe play poker, you know, something like that. So anyway, just giving you different mnemonic devices for the you know, you might have a test question like that, right? So I'm gonna give you blanks there. You need to be able to fill them in. Okay. Another thing, guys, you need to know this. This is also going to be. It's not going to be. So I'm not gonna like test you on this, but you're going to need to know this for the test. It's not like I'm going to ask you questions about it, but a lot of diagrams I'm going to show you of different rock outcrops are going to use different symbols to represent different types of rocks. Now that you've learned your igneous, sedimentary, and metamorphic rocks, you need to know how we represent them. So igneous rocks are usually showed some way like this, okay, with like X's. Usually I show it, this is usually how I show it, but you need to be able to recognize. So that's how igneous rocks are normally shown. This is how metamorphic rocks are normally shown, with these kind of wavy lines. Okay, the brick pattern here for sedimentary rocks, this is stuff you really need to know. For sedimentary rocks, the brick pattern is limestone. Coal is black, just solid black. Siltstone has these little like dashes, but with some dots in it. Okay, like that. Conglomerates show these large pebble-like pieces. Okay, shales are just these kind of flat, parallel dashed lines. Sandstones are these little dots. Okay, and they're meant to kind of represent the texture of the actual rock. So you need to know this stuff. Okay, because I'm just going to show you things. I'm just going to show you outcrops, and it's going to assume that you know this. Okay, what if I gave you a test question? I say, you know, when do you think, you know, take a look at the sandstones in the diagram below. You know, when do you think they formed in relativity to the shales? Well, if you don't know what a sandstone looks like and you don't know what a shale looks like, how they're shown, you know, like the symbols that are being shown, you're not going to know how to answer that question. So you need to know these symbols. Here's just some example of exam questions. A layer of sandstone on top of a layer of shale is younger according to principle of superposition. Okay. The surface below sedimentary rocks that overlie igneous or metamorphic rocks is called a nonconformity, right? So just some examples there. All right, that's all I have for you today. I know it's a long lecture. Do your lecture assignment this week. It's a biggie. It's a very important information. You know, this class is called Geologic History. These two lectures I've did this week are called Geologic Time. Are they important? Yeah, big time. Because everything that we're going to be learning for the remainder of the class is predicated and based on what we just learned this week. It's extremely important material. You need to know it. So do those lecture assignments. Do a good job on them. Don't skimp on them. I know it's going to be tempting. You're going to look at those assignments and you're going to be like, oh my gosh, how do I do this? Well, email me, figure it out, look at the videos. I'm going to put out a video explaining more how to do it. You need to know how to do that stuff. It's not going away. So anyway, that's my admonition to you. And hope you have a good week and enjoy the rest of your week. And I'll talk to you next time.